Just some rules of engagement. Please feel free to interrupt with questions, thoughts, comments as you feel free. It's going to be like a mush of a bunch of different ideas and papers that I'll talk about today. But broadly, the theme is essentially taking structure seriously in the context of deep learning. Required to start with a quote. Now I generate quotes from GPD. But essentially, you should think of a structural model in some sense, or structure, as being a set of assumptions that we bring to bear to a problem that we are trying to study, right? So there's data, and then we as the analyst or as the researcher are going to bring a set of assumptions, and I'm just going to call that structure. Mostly, I'm going to think about structure from an economics perspective, but it's not that we're only talking about economics. You can bring structure or domain expertise or any kind of informed priors, if you will, to bear on the problem from different contexts. So it could come from psychology, or from sociology, from engineering, from physics. I don't really care, but my examples are all going to be from economics and sometimes from business. Okay, just to get people thinking about this, let me start with the Lucas critique. So the Lucas critique is named after this gentleman by the name of Bob Lucas. Some of you may know him. He won that shiny medal that they give out in Europe someplace for economics. And his point was that if you want to make counterfactual predictions, you have to model the core primitives of the underlying data generating process. It's not enough to model data. You have to actually model the process by which the data has been generated at some very granular level. If it's data that was generated by humans, you have to actually model the behavior of humans. Otherwise, your predictions are not going to work out, or may be biased in kind of systematic or non-systematic ways. So the example kind of is, imagine that you incentivize your kids to do their homework by giving them ice cream, and then they learn the fact that they're going to get ice cream if they do their homework, and they game the system, right? And they shirk in order to get the ice cream to do the homework, right? So your model is no longer valid because the agent involved in the process changed their behaviors as a consequence of some of the processes involved. Right? This is broadly applicable across a variety of contexts. It's not just in economics, just in human behavior in general this shows up. So in order to kind of tackle problems of this sort, we have to think about structure, like what's the data generating process and what structure do we want to impose on that. And the way we do that is to start with theory, right? And the theory, again, by theory I don't necessarily mean kind of concrete academic theory. It could just be a set of rules that you impose. And they should articulate kind of the primitives by which agents in the model are generating data, if you will, or engaging in behaviors that then generate data. And primarily, the reason why we want to do this is we want to move outside of the data. Right? If the answers are within the data, then none of this is going to be relevant. So if you want to optimize actions, if you want to design policies, right, then you're going to move outside of the data in two ways. Either you're going to have to extrapolate, or you're going to interpolate in some ways. And we want to do that in kind of a principled manner, which is where structure comes in. And again, just to repeat myself, we model the data generating process. The data is just going to be useful in doing so. Okay? So that's going to the broad picture of what I'm going to kind of outline. One thing that kind of, just to put it out there, some of you know Sendel, and Sendel puts this as the Y hat, beta hat problem. So some problems don't need structure, right? Pure prediction will give you value, right? So if you can diagnose cancer just by predicting it, that's fantastic. But in certain other types of problems, you actually need structure in order to move forward, right? And I'm going to focus on those ones. And essentially, like I said, the key element is this idea of like interpolation or extrapolation, because if we can do that, then we can optimize. Otherwise, we're stuck, right? Now, a caveat here is if the domain is spanned completely within the data, if the data is discrete or the data is finite and bounded in some ways, then you can kind of traverse the entire decision space completely, and then maybe you don't need structure. But I'll show you examples, even with discrete data, where structure is going to play a huge role because of practical limitations of what you are capable of doing. Side benefits are going to be things like efficiency in terms of, well, if I can impose structure, the dimensionality of the problem can be reduced. I can learn things more efficiently. Okay? And second, and I'll show you this, is going to be interpretability, right? Because structure has meaning associated with it, it's easy to see the parameter or functional space and say, oh, I know what that is, because that's how you've set it up. It'll become clear as we go along. Okay, so just as an example, you can think of like what I'm calling structure as being, let's suppose we're interested in profits. This is really simple, right? Like just profits can be broken down into revenues and costs. We ask the question, well, what are revenues? Revenues is price times demand. Demand itself is a function. We can think of demand as being a number, a market size, which is n times the probability with which each customer buys. And that probability that each customer buys is a function of the prices we charge. And what we're trying to do is kind of figure out what prices to charge. That's kind of one example. I'll walk you through that example in a lot more detail. But now the question is, where is structure in all of this? Well, if we think of the probability of purchase as being a structural object, then it's designed from the ground up. We think of consumers or agents as making choices based on maximizing utility, and that's what generates probabilities. If you were a statistician or an ML person, it's just you impose a statistical model. It might be a logistic regression or something else. You don't think of that as being a process by which consumers make decisions. It's just imposed on the data, right? So that's what we're talking about. So let me try and kind of articulate my argument as to why structure is essential with a really simple example, and at least one of you here has seen this before. So imagine that there was an experiment that was run. This is going to be a case study that I'll talk about later. But for now, just think of it as a pricing experiment where prices were randomized. So it's a completely clean randomized control trial. Prices are randomized between $19 and $399, right? And you get this data. And your job is really simple, which is to understand what the demand curve looks like, which is how does the probability of purchase, relate to the prices we charge, right? Now, this was an actual application. There's more sophistication that will come later. But one of the reviewers suggested, hey, you know what? Why would you impose structure on this curve? You have enough data, right? Why don't you just use your favorite ML tool, like they suggested, a random forest? So great. And then that'll allow you to learn what this curve looks like non-parametrically, and you're home free, okay? Great. So now imagine what the problem is. Y is some function of price. It's as simple as that. It's like one dimensional. A simple curve is all you're trying to learn, right? Yes, David.
So Y is the conversion rate.
Y is the conversion rate, and then you've got prices. It's a randomized control trial. Everything is perfectly clean, right? You're just trying to learn a function.
And also, unless I'm missing something, the natural monotonic decay is there.
Right. Great. So now we're going to impose our favorite ML tool. We're going to say, okay, we're going to learn F using a random forest. I'm going to plug that into a profit function. My profit function is trivial. It's just margin times demand. And then I'm going to optimize. The optimal price for this will always be infinity. Not sometimes, always. Let that just sink in, right? And it's not complicated ex post. Once I tell you why, right, it should be obvious, because how do trees work? Well, their extrapolation mechanism, it's partitioning, right? So once I get to 399, I get to 400, and I say, what's the demand forecast for 400? What's the prediction for 400? Well, that's the same as 399 because it's partitioning. What about at 4,000 or at 4 million or at 4 billion? It's always going to be positive, which means set prices to infinity and you make infinite profits. Now, you might say, well, that's silly. I would never do that. And that's the point. You would never do that. You would impose structure. You would say, oh, the relationship is monotonic. You'd also say maybe there are shape constraints I want to impose. I want it to asymptote at a certain place. And all of those things that you bring to the table are outside of the data. They're not in the data, because the data is, you have tons of data. You would never learn it. And there isn't, more data will not help, because you take whatever experiment you want to run, I can always double prices and ask you what will happen then, and you won't be able to answer it. Right? Unless you have this mechanism of running an experiment with infinite prices or something else. You just don't know what would happen, right? And when you don't know what would happen, you're going to have to impose assumptions, and then you're back in my world, okay? Now, if I can't learn a simple one-dimensional function how can I learn anything else, right? And you can take this idea and you can run with it across a lot of things. You can take this to language models, you can take it to other ML contexts, but if you can't learn a simple function, right, then identification of more complicated things are called into question. Good. Yeah.
Hypothetically, I try to, let's say, impose a lower dimensional parametric structure, but then you would say, then I impose the structure.
But you want to impose. So my argument is impose that structure, because the trade-offs are going to be, like from a decision point of view, if you don't impose that structure, you're going to get infinite prices. Now, if you're lucky and you got infinite prices, you would recognize there was a problem. The challenge is going to be when you don't get infinite prices and you get something that looks reasonable and you get fooled into thinking that, oh, we have a reasonable solution. That's the dangerous one, right? Okay, so I don't have an impossibility theorem here, but it should be obvious that I can't learn structure from data. I'll have to impose something, some minimal conditions that will allow me to then make sensible inferences about what I want to do. Okay, so moving from structure to data, what I'm going to focus on today, this looks like messy, but it's really simple, right? This is essentially Bayes' decision theory wrapped into one equation. So the idea is, look, in order to make a decision to generate a personalized policy, that's the direction I'm going to go with, which is I want to use deep learning to generate personalized policies, right? And I'm going to use structure to do that. So I have an objective in mind. It could be profits, it could be welfare, it could be costs, whatever you want the objective to be. I'm calling it capital pi. And that pi is going to have a bunch of things in it. But what you're going to do with the pi is you're going to apply a criterion to it. So if it's profits, you're going to maximize profits. If it's costs, you want to minimize costs. And you're going to have some well-defined, space over which the decisions are going to be, explored. It could be finite, it could be infinite, it could be functional space. I don't really care. What's inside profits? Well, obviously one argument of that profit function is going to be the decision that you're going to perturb, and you want to know what would happen if. That's the counterfactual piece, right? Then there's going to be some squiggly term, right? Some psi or whatever you want to call it, the quantifier or that captures the uncertainty that's inherent, which you don't know anything about. You're going to bring some data to the table. I'm being very abstract here. And then there's this type, right? So I'm going to assume that there is a type of each individual customer. In my examples, it's going to be economic agents making decisions. I'll call them customers. And they have a type theta I. It could be a vector, whatever, right? If I have all of these pieces specified, then I can take this program, apply it, and I get an optimal decision for that individual I. Is that clear? Any questions about this? Okay. It's standard stuff. You're just integrating out the uncertainty, that's the expectations term, and you're making decisions. And this can be for firms, this can be for governmental agencies. You pick what your application context is. I'm going to show you a bunch of those if we have time for. Now, why do I focus on this? Because this heterogeneity is critical. If you want to, right? And there's many reasons why you want to calibrate this heterogeneity or kind of capture it. Obviously, if you want to personalize, you have to do it. Otherwise, there's no personalization if there's no heterogeneity. But even if you were not interested in personalization, but were interested in one uniform policy, we know from a bunch of research that we've done over the past 100 years that even the uniform policy has to be informed by that heterogeneity. Otherwise, you're not going to get it correct. Right? So today, what I'm going to talk about is more on the practice. I'm going to lay out some theory on the statistical theory around this, but I'm not going to focus on that too much unless you want me to. Okay, so now back to structure. So I'm going to go, my goal is to build these personalization engines and apply them, but I'm going to start by just saying, okay, how do we build in kind of deep learning into structure? So imagine you have a structural model. It could be anything. By structure, I just mean that you have a parametric per observation loss function that describes what you think the data generating process is. That's it. So it's actually way more lax than you think, right? So start with something that's purely parametric. And here you have theta I. The trick I'm going to pull, so you can ask, well, what do people usually do? In the applied literature, the most popular way of tackling this problem of figuring out what theta I is is to assume it away. That's like 90% of the research, right? Just there's no heterogeneity. Okay, we don't want that. So we're going to play this trick. So we're going to make theta a function of observables. Okay? And this is not, again, not a new idea. This goes back at least about 50, 60, 80 years, right? In different forms. Usually with a lot more kind of, you know, assumptions being placed on how theta of x is calibrated. But what we are going to do is take that old idea, right, and put a deep net on it, because I don't know the relationship. So think about what's happening here. I have some model. It could be as simple as a linear regression. Y is equal to alpha of x plus beta of x times treatment. But alpha of x and beta of x, I don't know what x's are relevant. They could be high dimensional vectors. And I don't know what the transformation is. So I'm going to just put deep nets as placeholders there. So there's a subtle difference that you should notice, right? I'm not modeling the outcomes y as a function, as a deep net of the treatment and the x's. I'm putting structure. That's all that structure is captured in L, my loss function. So it's a custom loss function that you have designed. It could be anything. It could be a likelihood. It could be a GMM objective function, a minimum distance, whatever you want your quasi-likelihoods, partial likelihoods, whatever you want to shove in there. You just have a loss function. And the only place the deep nets actually enter is where you don't have theory. So the relationship between y and t, by the way, y can be a vector, t can be a vector, t can be discrete, continuous, a mix. Anything is possible here, right? No assumptions at this point. Theta is where the deep nets enter. So it's very constrained in where the deep nets can go. It's only trying to inform you, or use the data to kind of inform itself about what the heterogeneity is. Right? Yeah.
If I think of, let's say, classical classification
Mm-hmm.
with logistic law.
Yep.
And now instead of using the linear model, we'll replace it with a neural network.
Yep.
And then now I got classifier as traditionally I would see as a neural network.
Yep.
And that would fit here.
No. So I'll go exactly to this problem in a second, and you'll see the difference, right? Okay. So here's, you know, a graph that should make it clear. So the red part, think of that as your parametric model. Think of that as the logistic regression. Y is 1 over 1 plus e to the power minus whatever t, right? That's what you would have. What we are doing is saying all the parameters in the logistic regression, those are deep nets. That's different from using a neural network as a classifier, because that would say y is some function, a deep net, whose argument is t.
X is different from the
T, exactly. So x is pre-treatment covariates that calibrate the heterogeneity. T is kind of the, you know, whatever you want to call it, is the treatment, or it's the variable that you care about, that you're going to optimize later on, if you will, right? And usually you'll have a randomized control trial, or you'll have some clean way of estimating the relationship between t and y. Now what we've done is all the parameters in the model, if it was purely parametric, there would be a finite dimensional vector of parameters. Now they are functional parameters. And we have to deal with that, with those functional parameters, right? So it's a little bit more constrained. We're giving up flexibility, but we know exactly where we're giving it up, right? Because of the problem where we can't learn the full function. So now the logistic regression will give you smoothing. It'll give you the ability to extrapolate. It'll give you the ability to interpolate, but we still have the flexibility in saying there's heterogeneity across agents, and that's going to be completely, you know, flexibly captured by the deep nets.
Going back to the case study, you would still retain some kind of a proper monitoring structure that in case to 0.
Right.
But
Now, across people, it'll be non-parametric. So it'll be parametric within person, but across people, it's non-parametric. And again, it goes back to this point that I was making earlier. The model that relates prices to conversion, that comes with theory. That's economic theory. How different people vary, I have no theory. That's just a fact of life. And so there, I have no assumptions that I'm imposing. I'm just using deep nets to calibrate heterogeneity. Yes?
So here, do you assume that y, t, and x are kind of independent? So that there's no relationship between...
No. Y is a function of t.
Y is a function of t.
Treatment affects outcomes,
Okay.
right? X is pre-treatment variable. So it's simple to think of this as in a causal framework, right? So there's t, which affects y, and it's moderated by x, but we don't know how.
Oh, I see.
Okay, that's the causal, like the DAG if you want to draw it out. There's like a million DAGs just stacked upon each other. Okay, yeah.
Kind of a related question. So in the special case of T being, say, like a binary treatment, this is like heterogeneous
Treatment effects. Perfect. So heterogeneous treatment effects are nested within the structure. Instead of using, let's say, causal forest, if you're familiar with those, now we have a causal deep net. But the advantage of this approach is we don't have to have T being even binary. We could have it be a vector and it'll still work. And all the theory, statistical theory that I'll show you is general. It'll just work. Okay. The estimator is pretty straightforward. Now we're just optimizing over functions rather than parameters. Okay? So we have to deal with that statistically. And I'm not going to go, but the advantage of this is, like most of you know how to code in Torch or in TensorFlow, this is trivial. We're just changing the loss function. We're informing, all the economic assumptions we're bringing to bear are only operating through that custom loss function. The rest you can just piggyback on everything that you know in Torch or TensorFlow or whatever else you use. Okay? So it's literally like lines of code wise, it's like 15 lines of code. It's not complicated at all. Okay, so let me just quickly convince you that this is okay from a science point of view to do. So what are the three pieces here? I'm going to approximate individual customer types or agent types with an estimated deep net. Okay, I'm going to break it up into three pieces. The first is, how do you know, or what I call the approximation part, which is that theta I can be approximated by theta of x. Okay, that's first. The second is the classic bias, or the second and third are the classic bias variance trade-off, which is even if their function exists, can deep nets capture it? Second. Third, even if deep nets capture it, can we estimate those deep nets and at what, right? How do we estimate it? So I'm going to have to give you rates and stuff, but I'm not going to waste too much time on it. I think I circulated that paper if you're interested. The first part is just I'm going to hand wave. My argument is going to be, look, the amount of data we have, by the way, if you've not seen this, this is all the variables that you can target somebody on in Facebook. Actually, that's just the first page. We're talking about tens of thousands of covariates that they have, right? So the history we have about customers, the history that we have about each of us, like, is massive, right? So the idea of like there exists other things that are missing is kind of silly, if you will, right? So I don't think there's much to argue here. Like, there are going to be contexts in which you don't have data, don't use this method. That's right. So use your judgment on it. What about the other two? That if you look at the paper, it'll have details. I'm going to skip that, but essentially, in a nutshell, as the complexity of your deep net increases, you're going to be able to, classic universal approximation theorems will hold, you'll be able to figure out what theta of x is. It's slightly weird because usually it's y that we're trying to capture. Now it's theta, right? So you just have to think differently. And the last part is, well, classic things is, can we estimate this at fast enough rates? Well, as n goes to infinity, at some rate, we can tell you what those rates are. Turns out that those rates are fast enough for semi-parametric inference, right? There's a paper that deals with that. The first paper is in Econometrica. There's a follow-up paper that shows you how you can actually apply this. Okay, and here's the rate. It's not optimal, obviously, but it's fast enough to do something useful with. I've already talked about this, right? But the last piece is going to be what Devrath brought up. So one, why use deep nets? Why not use forests or something else? You can. I can use splines. I can use polynomials. They're all universal approximators of different kinds. Deep nets are just practically really easy to do, right? The infrastructure to code these things up is so easy that it's like just right there. The other part people bring up is this, like this is not the audience that is subject to this criticism, but people usually think of deep nets as requiring tons of data. That's just not true, right? Just the same way like polynomials, learning like polynomials requires lots of data, but if you have finite data, you wouldn't use a 37th degree polynomial, you just use x and x squared. Same thing with deep nets, you can scale it down and yet capture meaningful heterogeneity rather than ignore it, right? So that's what I mean by kind of scalability. You can scale it up, you can scale it down depending on what the practical data kind of availability is. But the third piece is really the fun part, which is that it's structurally compatible. Literally, I can plug it in. So show you this. In economics, we start with a utility function. So the utility is a linear function of treatment. For now, think of treatment as price, right? So each person has an intercept, and their utility is a function of price, right? And some idiosyncratic shock, epsilon. And if you make the standard structural assumptions, it turns out that the probability of buying will be described by the logistic function, right? But the key point is that the motivation for the logistic function comes from this utility theoretic argument. It's not imposed, right? Now that's semantics, but it's going to be important for us. Now, the only thing we're doing next is we're saying, hey, look, we had heterogeneity, we don't know what to do with it, bang, we just make deep nets out of it, right? And to contrast this with if you were building a neural network classifier, it wouldn't look like this. It would be the probability of conversion is f of x and t. Okay? So the structure is the fact that we imposed the logistic structure on there. And that's going to give us something. It's going to give us nice, smooth stuff. It's going to kind of die out at a particular rate. It's all going to give it's going to be nice for optimization and all of that stuff. The bigger advantage, if you're actually doing economics research or any applied research, is look at the interpretability of beta. Beta was the effect of prices on utilities. It is still the effect of prices on utilities. Now it's just a function, but the interpretation never changed. I know exactly what it is. I can't go inside beta and tell you a story, but beta is interpretable by itself. Alpha is interpretable by itself. More than that, I can use alpha and beta to construct other economic objects, elasticities, profits, all of that can be constructed, and all of those will be, nothing changes. So if you've ever used these things for any kind of applied work, like you know that the log sum, for example, the partition function, the log of that is the expected welfare. I can still do that. Now I can do this in a heterogeneous manner. Right, so that to me is what I call structural compatibility. It's so easy to use it there. Okay, what about inference? Let's assume that you're interested in some statistic of interest. I'm going to run through this and get to the applications. I have till, what time do I have till? Like 5? Till 5? Okay. Okay. So imagine that you are interested in some statistic mu0, which is the expectation of some function h. We'll assume that that function is differentiable, right? And it's inside h is that true parameter theta 0. Right? So you want, and this could be anything. It could be profits, it could be counterfactuals. We provide a very generic influence function for this. So if you're not familiar with influence functions, it's basically we're saying, if I perturb the data in the direction, like, think of a Guiteau derivative, right? If I take the data and just perturbed it in some direction, what would happen to mu0? Turns out I can mathematically just write it down in closed form. More than that, I can evaluate all of this in TensorFlow or in Torch automatically. So I don't have to do anything at this point, right? I won't go into the details, but if you look at it, you can kind of recognize pieces from influence functions, other places like in maximum likelihood and stuff. But the key point here is there is a closed form influence function, and you can compute it completely automatically with no work. The estimator requires some amount of cross-fitting to get things working out cleanly, but let's let that be. And there's a central limit theorem. So now you can get standard errors, counterfactuals, standard errors for counterfactuals or for any other object of interest that you create using this, right? So it's not like general enough to do everything. I can't give you inference on anything that is x specific. So I can't give you inference on beta of x, but I can give you inference for the average treatment effect or group specific treatment effects. Any averaged quantity I can give you inference for. That's where the central limit theorem binds, obviously. Okay, let's get to the fun part, the next 20 minutes. I'm going to run through a couple and get to the main one. So I'll let, the first one is the toy, but not really toy. There's a billion-dollar industry behind this toy model, which is how do we target. So I'll skip this. But here's there's a replication. This is Sendel's stuff with Marianne and a couple of others. And the only point of doing this was to show you it can be done. Here the treatment effect, or the treatment dimension is large, right? So there's 12 different ad characteristics. So this was an application that they had where they sent out advertisements for a financial institution in South Africa. The data set is relatively tiny, 50,000 observations, give or take. The dimensionality of the treatment is 12 ad characteristics and 1 continuous offer, right? So that's a 13-dimensional treatment effect, which would be a nightmare to do, but pretty trivial to do here. We can replicate the results they had or check for robustness that we added heterogeneity. They didn't have it. The results kind of are in the confidence intervals contain their estimates. They should, because theirs was a randomized control trial. But we can do a lot more. There's massive amounts of heterogeneity in terms of how people react to interest rates. Just as a proof of concept, and there's also heterogeneity on how people react to different ad characteristics. Some people like pictures, some people don't like it, some people like the idea that there's information about competitor loan offers and stuff, some people don't care for it. Now imagine that you build up a profit function. The bank builds up a profit function and then tries to optimize it to find the optimal interest rate. It turns out that in this problem, the way I have set it up, the optimal interest rate is a fixed point, right? Doesn't matter. Everything just goes through, and I can give you a confidence interval for the optimal price to charge. I can give you a confidence interval for the profits that you will get if you imposed the personalized pricing policy or the personalized interest rate that, right? Again, just a proof of concept that you could do this. Here's an actual application rather than just a replication, where there's a published paper with JP Dubey, where there's a company called ZipRecruiter, and we ran this experiment. For 1 month, every incoming client of ZipRecruiter saw a random price between $19 and $399. I'll spare you the details of how the heck we got them to do this, but helps to have friends who are running the company. Once you know the structure, this is where structure helps, because I can write down optimal prices in closed form because I've put that logistic regression type structure in. I can estimate deep nets there with different architectures, check to see if it all works out. I can actually impose this back in the field and show you that everything matched exactly what we predicted. Revenues went up at the firm by 82%. Not hypothetically, actually went up by 82%. But more than that, I can do things like measuring welfare. Because I've imposed all of the structure, I don't have to kind of do complicated things to measure welfare. I can just use standard off-the-shelf techniques that you see in any textbook, right? And what's interesting is, as a side benefit, what we show is that in the paper, the point is to say that if you personalize, right, welfare can actually go up if you measured it correctly. Right? So just as a side discussion really quickly, the typical way welfare is measured is I take individual welfares and I linearly aggregate it. The problem with that is that treats every individual equally. So if you're rich or you're poor, you have the same weights. Those Pareto weights are the same. There's an entire literature on welfare economics. People like Amartya Sen, Jorgensen, who basically said that doesn't make any sense. That's why our tax code is not flat, right? Because we treat different people differently. If you impose, so they say rather than linear averaging, use the Holder mean, right? If you use the Holder mean, what they point out is that different powers in the Holder mean will give you different levels of inequity aversion. So if you as a planner are inequity averse, it turns out that personalization is actually good for customers. Why? Because now people who are affluent don't get weighted the same. So 100 poor people can't be dominated by one rich person, right, in terms of their welfare measures. Anyway, that was the point of the paper that you get out of it. The other kind of application of this that we're working on currently is to take the same structural model, push that, right? How far can we push it? There's an entire literature on game theory and applications of that in economics and marketing and so on. So we asked a simple question. What if personalization was a strategic choice? So imagine a world, and I'm running through it just to keep up on time. Imagine a world where a retailer has access to all the data. They own the data about their customers. But they can offer personalization as a service to 2 different manufacturers. And this is motivated by an actual data set, right, from Nielsen. How would they set those contracts? And what would welfare outcomes be for customers? What would profit outcomes be? And it turns out that here, as you simulate this often, there's variance depending on what happens. But mostly personalization emerges kind of as an ash, right? That both firms will choose to sign contracts. The retailer will offer personalization as a service with different fees for different manufacturers. They will both accept, and that will be the equilibrium outcome. And under that outcome, consumers will be strictly better off. It's not clear that they would be, right? Because imagine two different versions of personalization. If two manufacturers exist, you can separate. You can say, hey, you deal with these customers, I deal with these customers, local monopolies, prices rise, customers get screwed, right? That's one possibility. Turns out that's not what happens, because each customer now becomes a market. And competition intensifies at that level, and customers get lower prices, and they're better off. Right? Again, for this application, you'll have to, of course, verify this across different product classes or different contexts. But the key point here is, again, the reason you can do this entire analysis is because we can piggyback on all of the structural models that people have already built and now make them heterogeneous by inserting these deep nets really quickly. Right? Let's take, given all the craze about language models, it's kind of required that we talk about language models. So here's my version of a language model. Imagine that you want to ask the question. So here's, I get an offer for OpenTable. The question I'm asking now is, why is this message optimal? Right? And even if I clicked on this, right, there would be content. You can ask, is that content optimal? So I'm going to do this in the context of nudges. So those of you who've not heard the term, nudges is this idea that another of my colleagues, Dick Taylor, came up with. Again, he also won a shiny medal from somewhere in Europe. And the idea is to have very, low involvement nudges, if you will, on agents to get them to change their behavior without giving them massive incentives to do so. Okay. Typically, the simplest example of this is a reminder. I'm just going to remind you that you have a meeting. I'm going to remind you that and in this case, there's going to be a reminder that there is a form to fill out. Okay. But again, typically the way this is implemented by government agencies, by everybody else, is there's one nudge that goes to everybody. Why would that make sense? Right? You should have different nudges. But in order to do that, I need to know what people's preferences. If I'm structural, I need to know the preferences people have over language and how they're different across individuals. That's a high bar, but we can just build a machine. Right? How do we do that? Well, in this application, I was working with the SNAP program in California through an agency or an organization called Code for America. And the problem is very simple. Poor people, so people know about SNAP, it's the food stamps program. So if you're poor and you can prove you're poor, you get $200 per month per family member, right? It's an arduous process to get qualified. If you qualify, you get that, but 6 months after you qualify, you have to fill out a recertification form. If you don't fill it out, you might lose your benefits, right? Even in a state like California, there's a lot of churn, if you will, and they want to stop that. So they had actually imposed a nudge. So this is going to be our control treatment. It's simple. It says something like, hi, get CalFresh is the local California name for the food stamps program. To keep getting CalFresh, fill out a semi-annual report as soon as you can. It's required. Do it online. And this is not my research, but they had done some A/B testing to show that this was better than what they were doing before by about 13%, right? The question is, can we do better? I'm going to steal some ideas that you probably are familiar with. I wasn't when I started. This guy, Chomsky, came up with this idea of context-free grammars. Basically, it's like this, right? I'm going to move things around, right? I'm going to construct my own grammar for nudges by making the nudge modular. So let me show you what that means. Mary and John is feature number 1. Feature number 2 is got on an airplane, caught a ride. Feature number 3 is to Chicago, Boston. The reason I'm doing it this way, rather than using kind of generative AI, when this project was done, generative AI wasn't what it is today, but I need a bijective mapping for optimization. So I can't use, even today, I can't use generative models because it's not bijective. It goes one way, but I can't come back, right? People are working on that, but as of now, we don't have that bijective mapping. But this is. So the features are, and my grammar is blue before whatever that is, orange before green. That's my grammar, right? And you have to pick one feature at a time. So it's binary in each one. And now if I say 000, you can see the message. And if I said, Mary caught a ride to Chicago, you know that it's 010, right? Makes it bijective. Once it's bijective, I can optimize. Now here's a case where it's discrete. So where's the structure? We'll get to that, right? So here's my original nudge. I break it up into modular pieces, featureize them, right? And so now, for example, salutation, I don't know whether hi or hello. The consequence to keep getting in order for you to keep, in order to avoid losing, in order for you not to lose. So those of you who are familiar with prospect theory, you can see that's loss averse versus not loss averse framing. And there's a whole bunch of things. I won't bore you with the details, but my language can say approximately 14,000 different things. Okay? There are 19 features. Together, they span 14,000 possible messages with the meaning never changing. So I'm constraining the meaning. That's my structure. In addition, I have one other thing. I'm still going to use the stupid model, right? Because I just want to know did you fill out the form or not, right? And my features are going to enter exactly as before, but with deep nets. Now, why do I call this a structural model? Because I'm making a very strong assumption that the features are independent, there are no interactions. That's my assumption, that's my structure I'm posing, because if I didn't do that, I couldn't handle this problem. It would become too big to handle. Okay? There's not enough data to pull anything else off. The question is, does this help? Okay? So we still need to estimate stuff. So if we design an experiment, which we did using, yeah,
Features are the message that you send.
the message components. So feature number one is hi versus hello. It's a binary feature.
So personalization is at the message level, not at the person who's receiving.
It is both. It's going to be personalized to each person, and each person is going to get a different message depending on their type. And their type is going to be calibrated as a function of the characteristics that we know about them. So we have all of their data on, so California gives us Medicare data. So we can't use it directly to say, oh, you are qualified, but we can use it for this project.
So intervention has features, individuals have features, and you're sort of putting parameters.
Putting, exactly, right? So here's the model, right? So X is our individual features, F is the character or the message features, and you can think of this as a matching problem if you want. Okay, so it turns out that structure now helps, because if I want to design an experiment, I'm not going to run a whatever 13,824 armed bandit or something like that. It's just silly. I'm not going to do that. But there's only 19 features, so I only need 19 degrees of freedom. I'm going to do 20 or 21. And my sample size is about 15,000. I don't control that because these are the set of people who became eligible in a particular month for renewal, right? So, okay, if I run this as a test, I'm going to get the same kind of thing. I have control over here, and you'll notice that some messages are better than control, some are worse than control. So if you were doing A/B test, it's just a random draw. I have 14,000 different things. You would have somehow come up with A and B, and if you got lucky, you would end up here. And if you got unlucky, you would say, no, control is good, right? That's how we do A/B testing anyway. Somebody comes up with some idea. We're not going to use this for A/B testing, obviously. We're going to use this to estimate the parameters of the model or the functional parameters of the model and then optimize. And if you do that, you get this table, but the control message is right there. And point-wise, I can optimize because of my structure. It's actually trivial to optimize. So if I look at hi versus hello, I notice that hello on average has a better coefficient. So if I wanted one new message, hello should be in there. I can do it for every feature, and then I can just read it out. I can say, hello, in order for you to keep your CalFresh benefits next month, you must fill out an update by October 11th, do this now at. So it's a generative model, but it's also optimized, quantified, and I can tell you, if you use this message, what would happen. I can actually give you a prediction that, so it's jointly, it's coupled in some sense. Okay, so if we have that, but we have heterogeneity because we calibrated this with heterogeneity. Some people like hi and some people like hello. I have no theory why people like hi or hello. My theory is simply that people have preferences over language and that translates into their choices. Why they have those preferences is beyond me. But I can use that and I can say for a given person, score all 14,000 messages, 13,824. And then I can just pick the best one. Different people are going to have different best messages. Sometimes I'll do really well, sometimes I'll do, and control is nested, so I can see how much better than control. I can predict how much better than control I'm going to do. Right? So in this theoretical world, I can't lose. Now practically, whole other thing. right? So next month, we go to the field and we design a randomized control trial. So half the new customers or the new SNAP participants are going to get our algorithmic treatment, the heterogeneous treatment, if you will. 10% will get the original control. 30% will get the same random messages that I used before for learning. And then 10% will get one single optimal message, right? Just to see where people are. All of this got pre-registered with numerical values. So I'm not just registering it, I'm also saying, here's what I predict is going to happen. You can verify this is on the AER website. Now, my bad luck or whatever, good luck, depending on how you look at it, the month that this went out was November 2020. On the Monday of, but they have to send it out on Monday because that's what it is, that's how it's done in California. Tuesday is election day. So originally we thought, well, maybe we should push it to December, but then it's like, well, this is doomsday validation. If anything can go wrong, it'll go wrong here. And if it still works, then people should have more confidence. Did it work? And it depends on how you look at it. From the state of California's point of view, you got a 17% bump. From my point of view, it failed, right? Because it's nowhere near predictions. By the next month, things had improved up to 30%, but never got to where I thought it was going to get. Why? Because we figured out, thankfully I had done this 30 or these 20 random messages. Turns out that month over month, there's instability of preferences, but I can't articulate exactly why that instability exists. It could be that, there's shift in preferences because the set of people are not the same, obviously, and we didn't have enough people to fully calibrate the distribution of preferences. That's one possibility. Or it could also be that people's preferences for language are actually transient, and I would never know, right? But it still works in the right direction. It's just not as good as you thought it was going to be. Yes, David.
So these theta that you are learning in that of the table are some finite dimensional vectors, right?
The theta of x is a deep net.
This is deep net.
So for any set of x's, it'll spit out a theta. So it's right? So my prediction engine is to predict theta rather than predict y. Once I get theta, then I can do whatever I want with it to get my y. Was there a question up there? No. Okay. So I'm running out of time. You can do this in Spanish and Chinese and whatever else. This is not mine, but they tracked this over time to see what, and so Code for America did, and they found like over time it got better, and there's a shift from before for whatever that is worth. Again, I can value, so even though I'm claiming that it didn't work the way I said it would work, it did work, but just not the way I said it would work. But from an economic point of view, what happened? This is actual data, so this is not based on the model. You can just verify, you can see what happens by rescaling, kind of the standard kind of thing to do. And it turns out that about 14 in a year, if you followed this in California, your estimate, unbiased estimate of how much more money would go to poor people is about 14 million. I presented this at the USDA. I got invited to present it to all 50 states. And if you did this across the US, you're talking about $4.5 billion more that would go to poor people. It was already earmarked. It's just this would incrementally actually disperse that. And off that, if you look at kind of, even if you looked at only you might say like, look, you're comparing to something weird. What about from the optimal? Like even there, if you're only looking at personalization, you're talking about 1.7 billion more, right? This is serious money that would go. It's a whole other story as to nobody took me up even though I was giving the code away for free. We can talk about that offline, why that happened. So I'm right on time, but hopefully I'm giving you a few things to think about. One, that if you want to engage in counterfactual thinking or policy design, you're required to bring structure to the table. You are not going to be able to learn structure from data. And if data is being generated by human behavior, you will need structure. And embedding that structure, now there's various other ways you can do this. So I have done it by purely taking machine learning and embedding it into structural models. You could reverse it. You could say, I'm going to take a machine learning model and I'm going to constrain it with structure. Right? That's another approach. I think people in physics have been thinking about doing this. Right? The nice thing about deep learning, though, is it's super easy to do. I'm not saying it's the only way to do it. You can use other machine learning tools to do it, but this is trivial to implement. And it gives you, like this framework gives you everything you need for interpretation, but also for inference and a whole bunch of other things. Okay? So if you're interested, hit me up, but I think there's a ton of work that can be done in this space. So that's my story. Thanks.